This is worksheet number 7 of the atomic structure packet. And in worksheet number 7, we are going to learn how to do a calculation called average atomic mass. And this calculation requires some numbers and a calculator, but don't get freaked out. It's going to be the exact same method and same series of calculations every single time. So once you get it figured out, it's going to be relatively brainless. All right, but before we get into the calculation, I want you to kind of understand why we're doing what we're doing. Okay, in the video for worksheet 6, I introduced the idea of an isotope. The fact that there's these different versions of elements that exist, and they each have a slightly different mass. And when we look at the mass on the periodic table, we see a decimal because it's really an average of the masses of all these isotopes, all these variations of this one element. But I talked about how it can't just be a straight average. You don't just add up each of the masses of the different isotopes and divide by the number of isotopes there are, because some of the isotopes, some of the versions of the element are really common, and some of them are really rare. So instead, we have to find an average based on something called abundance, how common each of the isotopes is, along with the mass of that isotope. So we really need two pieces of information about each version of the element, each isotope. We need its percent abundance, so of all the atoms of that element, how many of them are that version, that isotope, and we also need the mass of that isotope. Okay, so let's think instead of about atoms, about people, because sometimes that's easier to see. Okay, let's say that I had in a classroom, we'll just make it small to make it easy. Let's say I had 7 girls and I had 3 boys. All right, and I said, today we're going to find the average mass of all the students in this class. Now, just to make the calculations easy, let's say all guys weigh 200 pounds and all girls weigh 100 pounds. I know that's totally unrealistic, but it makes our math easy. Okay, so could I just say, well, hey, I've got 7 girls that weigh 100 pounds, and I've got 3 boys that weigh 200 pounds. So I'm going to add up 100 plus 200 and get 300. And then because there's 2 different types, there's boys and girls, I'm going to divide by 2. So the average mass of all my students is 150 pounds, right? I mean, that's how we've learned to calculate averages normally in math class, right? But we kind of inherently know that that doesn't work because in this case there were 7 girls and only 3 boys. So we should expect the average to actually be a lot closer to 100 the way of the girls, right? Because there's a lot more girls. Okay? So the same is true with isotopes. Whatever version of the element is the most abundant, the most common, we expect that the average mass is going to be closest to the mass of that isotope. Okay, so let's go back to our problem with boys and girls, right? What we'd really need to do here is we'd need to take the mass of the 7 girls, so we'd have to do 7 times 100, right? And then we'd have to add that to 3 times 200, because we had 3 boys that weighed 200 each. And then we'd have to divide that by the fact that we had 10 total students, 7 girls and 3 boys, right? So if we were to do that, we'd end up with, let's see, I can do the math here, or maybe you can do it. 700 plus 600 divided by 10. Well, sure enough, when we calculate that out, we get an average mass of 130. A lot closer to the weight of the 100-pound girls than the average we calculated before when we did it more simply, which was 150, right? Okay, so we're going to do a similar kind of a thing here. And I think we'll go through problem number 2 together. Okay, now there is an example up here, and a lot of you guys might find it useful to refer to that because it kind of walks you through the steps. Okay, but let's just do one of your problems together. Number 1's kind of easy, so we'll do number 2. Okay, in all these problems, you're going to have 2 pieces of information. Okay, so here are your isotopes. You've got magnesium that we call 24, magnesium 25, magnesium 26. Now, those numbers are rounded, right? Magnesium 24, it actually weighs 23.985, which we've rounded to 24. Okay. And we've got magnesium 25 that actually weighs 24.9858, and we've got magnesium 26 that technically weighs 26.9826. Okay, so that's one set of information, is we're going to have the masses. Okay, and you can always tell mass because it's measured in these little mass units called AMUs. Okay, and then the other piece of information is we're going to have the abundance, which is always in percent. Right, how common is it? So for magnesium, of all magnesium in the world, 78.99% is magnesium 24. Right, so magnesium 24, that's definitely the most abundant. So we can kind of predict, because it's a good idea to have sort of a ballpark idea in our head, that our average mass should be the closest to the mass of the magnesium 24, that 23.985 number. All right, it should be closer to that than to like the magnesium 25 or the magnesium 26. So when we get to the end, we want to think about that and make sure we were sort of in the right range. Okay, so the first thing we have to do is these abundance numbers that are in percentages, we have to convert them to decimals because we cannot just go multiplying by percentages. So even if it's like a really small percentage, like in this problem down here, you see this like 0.27%, doesn't matter. You still got to convert it to a decimal. So what you're going to do is one of two things, whatever you're more comfortable with. Okay? You could take that 78.99 and you could divide it by 100. All right, that would give you 0.7899. You put it right into your calculator. Or if you just think it's easier and quicker, you can take that decimal and you can move it 2 places to the left. Either way should get you the same answer. This is equal to 0.7899. Okay, and so the 10%, you're going to do the same thing. You can divide by 100, or you can just move the decimal over, but you should get 0.1000. And same with the 11% as a decimal, that's equal to 0.1101. Okay, so your first step is to convert your percents to decimals. Your second step then is to multiply those decimals by the mass that they go with. So this 0.7899 is going to be matched up with the 23.9850, which gives us, I've already done this calculation, 18.9458. You should be writing this all down. Oops. And the 0.1 is going to get multiplied by 24.9858, which should give us 2.4986. And the 0.1101 is going to get multiplied by 25.9826. I try to leave 4 decimal places at this point. So that gives us 2.8607. Okay, so we've got those numbers. And now we are going to simply add those numbers together. So 18.9458 plus 2.4986 plus 2.8607. Are you understanding that most of you are going to probably want a calculator on this test? Yeah, start thinking about where you're going to get that from. All right, so we add them together, and if you did the calculation correctly, hopefully you got 24.3051, and we always put units of AMU, and that is our final answer. And remember, we made a prediction that we thought that the average mass should be pretty close to the magnesium 24 because it's the most abundant, most common. So this seems like a reasonable answer, right? If we had gotten like 26.98, that wouldn't really seem reasonable, right? If we had gotten 10, again, it doesn't quite seem reasonable. So you want to kind of like use your common sense when you check and make sure these answers are close to what you think they should be. Okay, so we will practice some more of these when you get to class next.